Hi everyone, welcome to my presentation. This is me Babu Dawadi from Tribhuvan University, Nepal. The topic of our article is ANFIS-based classification model for network device upgrade planning towards software-defined IPv6 network. Here, ANFIS means Adaptive Neurophagy Information System, and SoDIP6 means software-defined IPv6 networks. This is the joint research work carried out in co-authorship with the professor from our university, Tribhuvan University and Technical University of Valencia. This is the outline of my today's presentation. So our research is mostly related with the network migrations, that is the migration of existing legacy IPv4 networking component towards latest generation networking paradigms like SDN and IPv6, jointly known as software-defined IPv6 networks. As we know, the existing legacy IPv4 networking system has many problems of like address shortage, complexity of operations and management, security, quality of service, and many more. So for every service providers, it is required to migrate their existing network into latest networking like IPv6 and SDN to avoid all the issues related with the legacy IPv4 networking. But if we see the migration status worldwide, the IPv6 capability worldwide is just crossing 25% based on the ethnic IPv6 data statistics, and the SDN migrations in telecommunication and ISP network is still in the early stages. So the major dilemma for this migration are like higher cost of investment, lack of skilled human resources, lack of effective plan policies, lack of customer demand, and many more. So here we consider the cases is a two network, like a current network which consists of legacy IPv4 network and the future network, that is SDN enabled IPv6 network. So the migrations of those legacy components, that is switches, routers, and servers, means the transformations of those infrastructure into operable latest networking, in this case SDN and IPv6. So the major concern for the ISPs and telecommunications is to find out the status of existing devices before starting the migrations, whether those devices running are upgradable or they should be replaced to operate it with the latest generation networking. So for the large ISPs, there might be the thousands of devices which need to be inspected to measure its upgradability, because generally upgrade cost is lower than replacement cost. So the problem here is any service provider cannot provide the latest services with the latest networking standards immediately based on the customer demands. So it is required to evaluate the running infrastructures in terms of certain parameters. That means we need to apply some approaches to identify the status of their network devices, so that the planning for the migrations would be easy for the service providers based on the budget constraints and other human resource constraints and other things. So we choose adaptive neurophagy system to implement this, to solve this problem, migration problem, in terms of network device status identifications. So that the objective of this research was to implement an intelligent approach to classify network device routing status for its migration towards software-defined IPv6 network. So looking back into the literature reviews, there is a lack of migration planning with network device status identifications. However, ANFIS has a many multidimensional implementation, including several applications basically related to use for the estimation, prediction, and optimization, but it has a limited or no research works regarding the implementation of ANFIS in SDN and IPv6 networks migration. So we found one research by Mamulo, who applied ANFIS to classify the medical equipment replacement planning based on certain parameters like downtime ratio, maintenance ratio, age ratio, etc., where the author apply the scoring system. That means the raw data set obtained from the medical equipments are transformed into another format by applying the scoring, and the ANFIS is applied to identify that status. So we also followed this concept of implementing the ANFIS in the ISP network migration in terms of SDN and IPv6 network operation. So this is the proposed model in which we consider the ISP network here, which consists of set of legacy routers. So first we extract the device specific details and then maintain the knowledge-based system based on the device specific information, that is iOS firmware versions, IPv6 support, SDN support of those existing iOS of the device, extra memory slot available or not, and then end of life, end of support. These informations are also we just update it by gaining the details from the external domain also. Then those informations are fed into the dependency for this system. Here DFS simply get the information from the knowledge base and provide the preliminary decisions based on the IPv6 and SDN support of its existing iOS and firmware. Additionally, we capture the certain performance parameters like the CPU usage, unused memory, throughput, etc. From the real-time network using the SNMP agent, and those the informations obtained from the real-time network and the decisions obtained from the dependency fuzzy systems are mapped into the input data set, which are then transformed into another data format by providing the scoring system and fed into the ANFIS, which consists of 5 input variables and 1 output. So KB simply maintains the device details, including iOS firmware version with end of life and end of support of the device. So dependency fuzzy system provides the first level decisions by applying some fuzzy rules like whether the existing existing iOS firmware is upgradable or not. If upgraded, the new version supports IPv6 or not, and then if the device has an extra memory slot, so that we can add the hardware memory for improved performance, etc. So these based on this data set obtained from the real-time network and then the preliminary decisions option from the division systems. Basically, we implement those data sets taking the device information from the Cisco product. We consider certain series of Cisco routers, and then we generate more than 450 data samples, in which 60% data samples were used for training, 30% for testing, and 10% for validation. The data samples generated were transformed into the another format using the scoring system that is mentioned in this table, where the data values are divided into 4 ranges with the score from -16, 2, 3, and 4, where the higher value indicates the device upgrade and lower value indicates the replacement. So we also determine the threshold for migrations, that is if any parameters, input parameters is supposed to be -16, then it has to be replaced. Otherwise, if any parameter value is lies within the range of like 2, 3, and 4, and the output of ANFIS is supposed to be less or equal to 2, then it has to be replaced. Otherwise, the device can be upgraded. We also provided some weights into the input parameters. Basically, these range and the weight factors are defined based on the information obtained from the experts from the internet service providers of Nepal. So in the paper, we just provide the algorithm, that is algorithm 1, in the form of pseudocode. So I just try to summarize here as a textual form how we implement our work. Basically, we just take the network topology as a set of vertex and edges. Then we obtain the end of life, end of support, and memory slot information from knowledge-based system, and get the iOS firmware support status from the DFS, that is dependency for the system. And then other parameters like memory, CPU, and throughputs are obtained from the real-time operating device using SNMP agent, and then these two data sets are mapped into a single data set and transformed for the to make it suitable to input to the ANFIS model, where ANFIS is trained, tested and validated. Then the trained model provides the results as a status, whether to be replaced or upgraded. So the results is simply the network is visualized based on this evaluation. So this is the some glimpse of the training and the evaluation phases, where the input consists of 5 variables, as we already know that: end of support, end of life, memory, throughput, and then capacity, CPU usage capacity utilization. So while the training, the model is almost stabilized at 25 epochs. However, we run it up to 100 epochs. Then we evaluate the model with respect to check data. The check data and positive inference system output is now almost, we see the data and then check data and output seems to be almost overlap. That means it provides the correct result. For this ANFIS implementation, we follow Takagi-Sujino rules, which is more useful for mathematical computation and analysis, hybrid learning algorithm. And then the membership function used is generalized bell-shaped functions. We use the different functions like trapezoidal function also, but we get the better result with GBEL with the value of 2, which consists of rules 32 and the nodes are 92. So this surface plot simply provides the relationship of like a memory and end of life with respect to constant value of end of support, throughput and memory capacity. So this window simply provides the FIS output, that is positive inference system outputs, consisting of 5 input variables and 1 output. Here for the set of inputs like 2, 2, 4, 3 and 2, the output is 2.5. So based on our defined threshold, this value is greater than 2. That means the device is supposed to be upgradable. So based on the observed value and observed and predicted value plot, we see the result is best fit with the almost the 100% of R square value, that is coefficient of determination. Yes, we have established a complete simulation environment in Python to implement our trained model, for which we obtain the standard network topology from Internet Topology Zoo, and the topology as a graph is loaded into our simulation environment. Initially, each node and its performance parameters are randomly assigned its values, and then the network is started into the real time. So we integrated the MATLAB for geology toolbox into the Python using the MATLAB engine API, and then after running the whole system, the network is visualized using the matplot-like model. So the visualization shows that the upper figure here we can see the Evelyn network, where the red color node indicates the device is to be replaced, and the green color node indicates that the device is to be upgraded. This is the additional implementation and verification of our proposed model through the implementation on standard network topology. So with this, I just want to conclude this resource that the IPv6 and SDN are the emerging next generation networking paradigms to be considered for legacy IP network migration. For the migrations, basically switches and routers are the major networking components to be considered for migration. So we implemented ANFIS, an intelligent approach to classify network device for the transformation of legacy IP networks into software-defined IC networks. So the presented approach outperforms well in terms of accuracy, and we also verify our works with the standard network topology, that is Evelyn and Gen 2000 network. Definitely there are some certain limitations in our work. We are particularly confined to Cisco, certain series of Cisco IP routers. So for other vendor products, it may be required the separate training of the model and separate assumption in data preprocessing. We also consider the network from the perspective of migrations. The data set defined are based on the SDN and IPv6 support and its migrations. So for the regular maintenance planning, maybe we need to consider for other data like downtime ratio, age ratio, etc. So training of the model and compare the performance with other machine learning algorithms like ensemble tree, SVM optimizable, fine tree, linear regression, etc. are also considered as the future works. Finally, I thank you all for your patience listening my presentations. We would like to acknowledge those organizations for the partial funding support of the research. So if you have any questions, please, you are welcome.